Today I'm going to talk about gVirtualXRay. This is an open source library that I've wrote to simulate X-ray images. So that's a talk I gave at image-based FEM for industry in Swansea on the 5th of September. So first I'll start with some statements. So part of this project's been funded by a grant like Sept, where I developed some stuff for positron emission tomography. And another part, a demo has been partly written with funding from another FP7 project, Resimus. The graphics card that I used was donated by NVIDIA. So NVIDIA got a scheme where they can donate some GPUs for research. And I thank Jean-Michel Leton from INSA for his support during the data acquisition. So he was my MRes supervisor back in the days. So I'll give you some background, because this is not something that been done in just a couple of weeks. It's quite a large project. So we know that X-ray simulation has been studied a lot in physics, and there are several codes available to simulate X-ray imaging. But very often they rely on Monte Carlo methods on CPU, and very commonly used in dosimetry for radiotherapy. This provides very accurate images, results, but it takes a very long time, even on today's computers. So there are some alternatives, such as ray tracing, but it's still relatively slow on CPU. So we came up to the conclusion that a fast open source library on the GPU was needed. And I worked a lot in VR, virtual reality, for medicine, like to train radiographers or radiologists, anesthetists, and so on. So here we focus on the speed, not necessarily on the accuracy, but we'll show that we can still provide accurate images. So in 2003, Nicolas Freud defended his thesis on the modeling and simulation of X and gamma ray imaging systems, where he started to use computer graphics algorithms and turn them into something that can be used to simulate X-ray images. That was all written on the CPU. At the same time, I worked on the modeling of the response of an X-ray detector and tried to remove some artifacts in 3D micro-tomography. It's only in 2004 that GPUs started to be programmable, so the OpenGL shading language appeared in 2004. And from there I had in mind that, well, I could port some Nicolas Freud's work to the GPU, because, well, this is using the same algorithms. So in 2008 I did my PhD, and I initially worked on ultrasound imaging, but soon I decided, well, I could also do fluoroscopy, like simulate X-ray images to guide needles to train radiologists. So fluoroscopy is real-time X-ray images. So I started to work on this, and then we started to have a simulation package in 2008-09. I did some more physics to it, 2010. In December 2013, I decided, well, instead of having this code that sits on my computer, I'm going to turn it into an open source project. So I started to rewrite all the code and make it bomb-proof, so that it could be used pretty much by anyone. It took a couple of years, and now we start to have something that's quite decent. So this is fully open source, that's hosted on SourceForge using an SVN server. It's implemented in C++ using OpenGL. For this conference, I started to rewrite the code so that it could be used in Python. So there is a Python plugin now. Perform very well, so it provides real-time performance, and we try to do some quantitative validation to show that this is accurate. And because it's open source, my results are reproducible. I use photon cross-section from NIST so that we got good inputs for attenuation coefficients, and the geometry that we use to simulate objects are polygon meshes, and we support popular formats via a library as Sept, and we can use STL files, PlyFi, 3ds, OBJ, etc. So if you look at what happens, so when X-ray photons cross matter, they may interact with the object or not. So photons noted as 1 are the photons that directly reach the detector from the source without no interaction. And photon 2 can be absorbed, so they don't contribute to the image. They can be scattered, so the path of the photons are changed, and so we introduce some blur or noise in the final image, and they can be scattered and absorbed, so they don't contribute again to the image. So really what is very important for us are the photons that are directly transmitted. So, and this is something we can do quite fast on the GPU. So there's a very well-known attenuation law that is written as this. So we got an X-ray source, photons got an energy, we got a given number of photons of that energy, and for all the different layers of material, we need to know how much the photons are crossed for each material and the material property of every layer. So the mu attenuation coefficient, that's a linear attenuation coefficient, and that will depend on the energy, the material density, and the atomic number of the material. So these are parameters, and really what we need to compute is this in order to solve the attenuation law. So if we consider a very naive approach, we have a ray that is going to cross the material, the sample here, and we're going to find the different intersections. And the order of intersection may not be the one that we want. So we want the distance between 4 and 1 and 3 and 2. So we could sort the intersection on the GPU. There is a technique called depth pilling, that a multipass rendering technique for transparent objects. But that will take a bit of time, and we can show that this is not needed. Because in computer graphics, we know that normals are outward. And if we look at the dot product between the normals here and the viewing vector v, we can see that the dot product is negative when the ray leaves an object, and it is positive when it enters an object. So to compute the path length, we only need to solve this equation. So these are given, this is given as well. So we need to compute di, which is the distance from the X-ray source to the intersection point. And we do all that in a shader program. And then we do compute the sign of the dot product, do that product here, and the sigma, the sum here, can be efficiently performed using the OpenGL blending function, making sure that we use high dynamic range rendering. So we want values that are not only between 0 and 1, because traditionally on the graphics card, pixel values will be between 0 and 1, but we can exceed that with high dynamic range imaging rendering. So we're going to use 3 FBOs, frame buffer object, which you can consider as a temporary image that is stored somewhere on the graphics card. So first we compute the path length for every object, then we do the product and the sum in another one, and finally when we have processed all the objects, we can compute the exponential and that product. And then if we want, we show the image, or we retrieve it from the graphics card to save it in the RAM. Then we can add the beam spectrum, so have one more than a single energy in the beam spectrum. And basically what we do, we iterate for all the different energy beams. So all the bars here would be like one iteration of extra iteration of that simulation. And we can do the same to take into account the focal spot of the X-ray source. So we could have a parallel beam if the source is very far away from the detector, or very small point source. But really we could have something that's a little bit more than a point source. Like here it's a cubic millimeter. And basically what we have is an array of a cube of point sources. And we're going to iterate through these sources. So in addition to the previous pipeline, we added 1 loop, 2 loops, 3 loops, 4 loops. And that's going to make the simulation a little bit slower. So we want to make sure that it's not only fast, but that the images are accurate. So we simulate the Beer-Lambert law, and to do that we rely on linear attenuation coefficients. This is not necessarily known because actually we use a mass attenuation coefficient, mu over rho, and the density. So really what we want to make sure is are our values of mu and mu zero over rho accurate. Then is the Beer-Lambert law implementation accurate? And finally, are the images that we simulated accurate? So because I focus a lot on medical applications, in medicine we like Huntsville units to represent the properties of voxels, and there's a very well-known paper in the radiotherapy community that provides a correlation between CT numbers, Huntsville units, and tissue parameters like density in that case. So here's from the paper, this is for more simulation, and we can see this is the same. We know how it's computed. So this is the issue numbers are independent of the energy, and this is why they are actually so popular. So they are estimated at a given energy. So we got mu water and the mu of the material. So if we know the mu water coefficient for any energy, we could inverse that and retrieve the mu parameter for any energy for any Huntsville unit. So that's the theory. And that's what we did here. So if you have a linear interpolation, we can see these bumps here. So actually we need a log-log interpolation. And now we got a very accurate mass attenuation coefficient. Here is for soft tissue. We do the same for bones, which are more attenuating. And here you can notice these peaks here. And they don't appear in the mass attenuation coefficient of water. So let's see what happened. Well, in that case, we can't retrieve the peaks because they are not in the data. So this model is simplistic. It's not going to work. So this is why we have to move to use photon cross sections from the XCOM database. And now we did that, we can retrieve mass attenuation coefficient for the bones here. So that quite work. So now we know that the attenuation coefficients are accurate, we can assess the Beer-Lambert law. So we just consider the polychromatism case. So we got 10 photons of this energy, 20 of this energy, 10 of this energy. The cube here is made of soft tissue and the cylinder of bone. So we're going to simulate an image and we're going to look at the central pixel. So we solve the attenuation law by hand using a calculator, and this is what we got. And we did the same on the GPU using the simulation library, and this is what we got. And the relative error is about 0.1%. So we can conclude that this is pretty much the same. So now we're going to simulate images using our library and the library from CERN, GEON4 via the GATE framework. GATE is very well known in radiotherapy, and that makes using GEON4 a lot easier. So we do those two simulations, and then we compare the two images to see if they're the same. So this is the same object, this is our detector, and here's the source. And this is what we got using GEON4 on HPC wells, and that took about 2 weeks to get, and you can see the image is noisy. This is because that's Monte Carlo. That was something to expect. Using our library, it takes less than a second, and there is no noise because, well, this is deterministic. So we can conclude that the two images are the same because the cross correlation is about 100%. So here we're going to move the source, so it's not centered anymore. So same again, about 2 weeks on the CPU on HPC was using GEON4, less than a second with our library, and the cross correlation is about 100%. So the two images are the same. So now we're going to use a cubic source. And you can see the blur appearing here, and the blur appearing here as well. And the cross correlation is about 100% again. So as a conclusion, we know that all images are accurate. So the library has been used in some small projects. So here is with a PhD student from Spain. He's coming, like, he came 2 summers to work with me to develop a radiography tool to train radiographers. And basically, it's instead of having a textbook, we could have a virtual environment that could be used in the class, in the lecture theater. We can take as many X-ray images as we want. We can move the patient as well, and we can do different poses, different parameters of the X-ray machine, different collimation, and you can do a lot of things that you won't be allowed to do on a real human because of the radiation dose involved. Other things that the PhD student did was to add coins in the stomach. Let's say you got a toddler that's putting things in his mouth, and that could happen. And well, we can't train radiographers on toddlers and make toddlers eat coins. It's not acceptable. But we can do it safely on a virtual environment. So we have another guy in Spain, I can't remember which university. So he was using it a lot for his PhD, and now he's a lecturer. He wants to use the library to teach medical physics. So we could simulate very simple projections and also tomography acquisition and show how the reconstruction algorithm work. So we got the X-ray source, the detector, an object here, we don't know what's inside. We take a lot of X-ray images around that object. So here are our X-ray projections. We transform them into sinograms, unfiltered, filtered, back project them. When it's not filtered, it's very blurred. When it's filtered, we can have a very nice image. Just the same as in on a medical scanner. Another project estimates the respiration motion in real time again. We show that it can be quite accurate, and if you combine respiration and CT, well, we got fluoroscopy like here, so you can see the lungs deforming here, a very shallow respiration, so the ribs are not moving very much, but this is moving. This is diaphragm here. And if you combine CT acquisition with respiration simulation, you can start to see things that will happen in real case scenario. So here's without respiration, here with respiration, and you can see here the reconstructed image is quite nice. Here we can start to see these things appearing, and here as well some problem. This is called ghost artifacts. It's when the patient don't hold his breath and start to breathe during the CT acquisition. That's something you will see in medical images. So if we focus more now on material science, so I'll start with a very simple Python program. So what you need is to create an OpenGL context. So you can create a window that you show or that you don't show. Set up the position of the source, the type of source, here a point source, a parallel beam, and the spectrum of the beam. So here I decided to have a monochromatic spectrum of 80 keV. And there's only one photon in that spectrum. Then the parameters of the detector, so the position, its orientation, the number of pixels, and the resolution. Then we load some data, so we got a collected file, and the data is recorded in millimeter. And for every meshes in that same graph, my linear attenuation coefficient is 0.5. I make sure this is in the center, some artifact filtering, just in case there's some problem with the normals, compute the image, save it as an NumPy array. You can have an interactive loop so we can interact with the program to see what's going on. Because we got an NumPy array, we can save it, so we can save the X-ray image on the hard disk, and we can plot it with very popular tools such as Matplotlib. And if we see, we can try this the same on using Python. So this is the same program, and this is what happened when we run it. So this is okay, so we got our X-ray source here, the detector here, and a 3D mesh here. So I can hide the beam here by pressing B, and I zoom in, and when I press W, you can see the triangles. So it's W for wireframe. The image can be displayed in negatives. That's what we've done here. It's because it's popular in medicine, but if you press N, it could be turned into a positive image. Then I quit the interactive mode and displayed it with Matplotlib. And I should have it on the hard disk as well, so I can use popular tools such as ImageJ. And here is the X-ray image. And we can do whatever we can do with ImageJ, log scale, adjust brightness, contrast, and so on and so on. So I use Python to do an application about material science. So we're going to focus on 3D micro-tomography of a tungsten fiber, and the data has been acquired at the European Synchrotron Radiation Facility in Grenoble. So we're interested in that little object. Here is a euro coin. That gives you an idea of the scale. So some tomography were perfect. So here we got a fiber, but the core here is in carbon. It does not attenuate attenuate X-rays a lot. So when we change the carbon into tungsten, they start to see these artifacts. All these streaks here, these dark lines, they do not exist in real. So my work was to see what we could do with simulation to figure out what went wrong. We consider, well, the scientist who took this image considered that the beam was monochromatic and that the camera was very good, so both were discarded as the source of artifacts. So first I took another CT slice, this one, and I'm going to try to do a lot of simulation to recreate the same object using optimization. So I took some projections from the acquisition, and then I'm going to simulate a square and deform it, move it around so that is a the projection of that cube match these projections, or the reconstructed data match this CT image. And I've written a very simple evolutionary algorithm, like a genetic algorithm, in Python, without anything complex, just to show a case study. I did not have much time, so took a lot of X-ray simulations here, and in the end, after the optimization, we can see that our cube is located and scaled to match this object. Here is the error, and it's quite a good match. You can see the projection difference here. So the reference image, the simulated cyanogram here, and the difference between these two. Same as the reference CT, the simulated CT, reconstructed from this, and the differences. Now, we want to have the tungsten fiber, so we're going to use a fly algorithm because this is very popular to this is an algorithm that is used to find 3D points in the space. So we're going to optimize the position of endpoints representing the centers of cylinders. And to know how good are these points, we're going to use a leave one out cross-validation. So again, we can work on the projections or on the reconstructed images. We run it with a lot of points. In the end, we iteratively remove the bad points, and this is what we got. So the reference here, the simulated data, and the differences. And we found 6 out of 6 points, and there are another 2 that did not exist. But again, with a very simple algorithm, this is a good match. With a more complex implementation, I'm sure we could have been able to get more accurate results. Then, well, we did some experiment at the ESRF to get the edge spread function so that you have an idea of the PSF. Moving edges technique, we did it along the horizontal axis, both direction, and vertical axis, both directions. We extract the profiles, reconstruct the profiles from different pixels, and do a fit of this data with a curve, so this model. Then, using the derivative, you got the edge spread function, which is could be used as a PSF. So now we take the same data, do the projection, do a convolution of the projection with the EFF, and then do the reconstruction. So here is without convolution, with convolution. And you can see we start to see some streaks that we saw in the real image. So even if the camera is very good, the ESF is almost a Dirac, we can't discard it. So now we're going to take into account the polychromatism, so the harmonics in the beam, and we only got 3% of harmonics. We'll see that this is enough to generate artifacts. So here is with harmonics without convolution, with harmonics and convolution. And in both cases, you start to see the same streaks. So again, even if the beam is almost monochromatic, you can't discard the polychromatism. So as a conclusion, I say we got a C++ X-ray simulation library, which is open source, works in real time, is portable, works on Linux, Macs, and Windows, and is validated. There's still some work here, but I'm getting there. We have different shapes of beam, point source, cubic source, parallel beams. It could be any kind of shape. The spectrum can be monochromatic, polychromatic, can be used in various applications, in virtual reality for teaching, or as a virtual testing lab, as in the material science application. Future work, well, I want to add more so that it's easier to have compounds and mixture selection for the materials, add unit testing so that we show that the library is robust, add a bigger user list, maybe work with volumetric meshes for tissues, like in medicine, because, well, we know that bones are not homogeneous, for example, and I can add some stuff that are asked by users, like, well, I use C++ a lot, but also MATLAB, Octave, Python. Python is done now. And I'm happy to have new application and collaboration.